Alright, geometry, lesson 18, looking more carefully at parallel lines. So we've spent a lot of time with parallel lines, a week or two ago, just talking about what they are and talking about how angles are congruent when you have lines parallel. When you have lines parallel with a transversal, if you know they're parallel, you know that angles are congruent, other angles are congruent, these angles are congruent, etc., etc. Then we spent a lot of time talking about if you have two lines with a transversal, if the angles are congruent, then the lines are parallel. We're going to get a little bit deeper into that today and discuss it further. So first of all, opening exercise. Exchange problem sets from lesson 17 with a classmate. Solve the problems posed by your classmate while he or she solves yours. Okay, go ahead. We're gonna do this in class tomorrow. You'll have time to do it. It'll be part of the problem set packet you turn in for a grade. So we're gonna exchange some stuff. What we want to talk about today, though, is we say that two lines are parallel if they lie in the same plane and do not intersect. Two segments or rays are parallel if the lines containing them are parallel. Here, two segments or rays are parallel if the lines containing them are parallel. So I have, line 1 is parallel to line 2. If I have segment AB on line 1, we should say these are parallel, and segment PQ on line 2, if line 1 and line 2 are parallel, then segment AB is parallel to segment PQ. Okay? So that's what we're talking about today. Well, no. We're going to use this information to talk about parallel lines today. All right. Why is the phrase "in the plane" critical to the definition of parallel lines? Explain and illustrate your reasoning. This means draw a picture. I actually think it's much easier to explain this one using some tools. Okay, we're going to use pencils. These are two lines that are in a plane. This piece of paper is a representation of a plane. So I have two lines lying in a plane. I can say that these two lines are parallel because these two segments are parallel because if the lines extended out forever, they would never intersect. I could pick this pencil up and put it over this one. Now they are still in a plane. There is an imaginary plane, invisible plane between the purple pencil and the yellow pencil that I can say these two segments lie in a plane and they are on lines that are parallel because they never intersect. I could go out this way. Now I have a diagonal plane through the two segments, and these two segments are still parallel. Is there any way that I can make these two segments not intersect and not be parallel? If I turn them like this, they are no longer sharing a plane, but they will never intersect. Okay? If I laid them on top of each other, or even if I went like this, the segments are part of lines that now intersect, and they're on the same plane. But if I pick one up, now they are no longer on the same plane and they will never intersect. So the definition of two lines never intersecting is not a valid definition of parallel. They have to share the same plane, like that. Okay? And here would be an illustration for you. Two lines, three-dimensional space, are called skew lines. This is a very important definition. Circle it, highlight it, whatever you need to do. If they do not lie in the same plane. In that case, they do not intersect because if they did, they would share a plane together and are not parallel. If they were parallel, then they would both have to lie in the same plane. So what we see here is like that, okay? So there's skew lines because they do not lie in the same plane. The yellow pencil and the purple pencil are in different planes. They do not intersect because if they did, they would share the plane together. like here, and are not parallel. If they were parallel, they would both have to lie in the same plane and never intersect. So a new word. Okay. In Lesson 7, we recalled some basic facts learned in earlier grades about pairs of lines and angles created by a transversal to those lines. One of those basic facts is the following. Suppose a transversal intersects a pair of lines. The lines are parallel if and only if a pair of alternate interior angles are equal in measure. Suppose a transversal intersects a pair of lines. Those lines are parallel if and only if a pair of alternate interior angles are equal in measure. So we'll label them. If the measure of angle 1 is equal to the measure of angle 2, then line 1 is parallel to line 2. Our goal in this lesson is to prove this theorem using basic rigid motions, geometry assumptions, and a geometry assumption we introduced in this lesson called parallel postulate. Sorry, we introduce in this lesson. This is what we're talking about today. Of all the geometry assumptions we have given so far, the parallel postulate gets a special name because of the special role it played in the history of mathematics. The history is, Euclid included a version of the parallel postulate in his books, and for 2,000 years people tried to show that it was not a necessary assumption. Not only did it turn out that the assumption was necessary for Euclidean geometry, but a study of the parallel postulate led to the creation of non-Euclidean geometries. Okay, moving on. All right, the basic fact above really has two parts, which we prove separately, okay? This lesson is a bit long because we're doing each one separately. So first of all, suppose a transversal intersects a pair of lines. So this is number 1. If two alternate interior angles are equal in measure, then the pair of lines are parallel. So what we're going to prove is if the measure of angle 1 is equal to the measure of angle 2, then line 1 is parallel to line 2. That's number 1. The second thing we're going to say is suppose a transversal intersects a pair of lines. If the lines are parallel, so we're going to say if line 1 is parallel to line 2, then the measure of angle 1 is equal to the measure of angle 2. So if the lines are parallel, then the pair of alternate interior angles are equal in measure. The second part turns out to be an equivalent form of the parallel postulate. To build up to the theorem, first we need to do a construction. All right, given a line L and a point P not on the line, follow the steps below to rotate L by 180 degrees to a line L prime that passes through P. So first, label any point A on L. Then find the midpoint of segment AP using a ruler. Measure the length of the segment and divide it in half, finding C. That doesn't look right. Let me double check it. Yep. Now draw this line. All right, find the midpoint, distance, label the midpoint C. Perform a 180-degree rotation around center C. To quickly find the image of L under this rotation by hand, we're going to do the rest of it. Hold on. I'm going to draw a circle. I should pause it. My lead is coming out. technical difficulties. I think I might have to redraw that other half. Ah! All right, so center C. It's actually easier to not press very hard. Try to keep the middle point, but nice and gentle with the lead. All right, draw C, B. Oh wait, pick another point B on L. Draw CB. It's a line, so I'm going to extend through C. I just drew line CB. Draw a circle, center C, radius CB. I have to make this a little bit bigger. If I would have put B on the circle, it would probably made my life just a little bit easier. All right, label the other point where the circle intersects line CB by Q. Draw PQ. There is line PQ. Okay, let's see what's next. You see on your paper, label the image of the rotation by 180 degrees of L by L prime equals R. Rotation of 180 around C, L. So we're going to label this L prime. Okay, that's what it says right here. All right. How does your construction relate to the geometry assumptions stated above to rotations? Complete the statement below to clarify your observations. Okay, I'm going to point to each thing as I say it because it can be confusing to read. The rotation about C, 180 degrees, is a 180 degree rotation around C. Rotations preserve, oh goodness. Not having luck with that pencil. Lines, therefore, the rotation about C, 180 degrees, maps the line L to the line L prime. What is the rotation about C, 180 degrees of A? Let's look. So A, 180 degrees, we're going counterclockwise, remember, becomes P. All right, example 3. I think there's 6 or 7 examples. So I'll say now, if you need to take a break midway through this lesson, it would be a great lesson to do so. It's going to be a little bit long recorded, and it's hard to keep your attention for a really long time. So if you need to take a break, please take a break. Just remember the time that you take a break and come back and push play at that time again. All right, so the lines L and L prime in the construction certainly look parallel, but we do not have to rely only on looks. Okay, as I've taught proofs in the past, because I said so is never a reason, because it looks right is never a reason. We need mathematical reasons for everything. So, claim, in the construction, L is parallel to L prime. This is what we're trying to prove. Okay? Proof. We show that assuming they are not parallel leads to a contradiction. If we assume they're not parallel, we're going to have a problem. Okay? We're going to have a contradiction, and contradictions aren't good. So we're going to show that right now. We show that assuming that they aren't parallel leads to a contradiction. If they are not parallel, then they must intersect somewhere. We call that point X. We need to find X, which is where they intersect. Since X is on L prime, let me get my drawing back out. Okay, X would be on L prime somewhere, because that's where they intersect, right? That's our contradiction. Since X is on L prime, it must be the image of some point S on L. So if these intersect, they would intersect at X. And X would be somewhere on L prime, which means the image would be somewhere on L, right? Because it has to be 180-degree rotation. If we go this way, it would be somewhere on L. Back over here, we'll say S. Here we are. So let's rewind a little bit. Call that point X. Since X would be on L prime, it must be the image of some point S on L under the rotation about C 180 degrees rotation. So we're going to say that the rotation about C of 180 of S equals X. Or I could say the rotation about C 180 of X equals S. Since the rotation about C 180 degrees is a 180-degree rotation, S and X must be the endpoints of a diameter of a circle that has a center C. Just like A and P are on a diameter with a center C of our circle. S and X would have to be on this big circle with center C. Since S is a point L on L and X is a different point on L, it was the intersection of both lines, we have that L equals SX because there is only one line through 2 points. But SX also contains C, which means that L contains C. However, C was constructed so that it was not on L. We constructed C. It's not on L. It's not on L prime. Okay, it can't happen. And then we say that X is where L and L prime are supposed to meet, yet X has to be on L, has to be on L prime, but it also has to have C on L and L prime. But we made C not on anything. We made it that way. There's only 2 possibilities for any 2 distinct lines L and L prime in a plane. Either the lines are parallel or they're not parallel. Since assuming the lines were not parallel led to a false conclusion, the only possibility left is that L and L prime were parallel to begin with. We be good. Awesome. All right, example 4. The construction and claim together implies the following theorem. This is important. Given a line L and a point P not on the line, there exists a line L prime that contains P and is parallel to line L. Okay, we started out with line L and P that is not on the line. And then we constructed line L prime that is parallel to line L. This is a theorem we have justified before using a compass and a straight edge construction. Okay, that's how we did it. But now let's see if it follows directly from basic rigid motions and our geometry assumptions. Okay, to do that, we now have example 5. We are now ready to prove the first part. It was all that work just to get to part 1 of the basic facts we did above. We have 2 lines, L and L prime, and all we know is that a transversal AP intersects L and L prime, such that a pair of alternate interior angles are equal in measure. In the picture below, we're assuming that QPA, which I labeled 1, and BAP, which I labeled 2. The measure of 1 is equal to the measure of angle 2. Let C be the midpoint of segment AP. Okay, we've measured it a few times, actually just once, but it's an inch long on my drawing. Okay, so about a 1/2 inch. There is point C. What happens if you rotate 180 degrees around center C? Is there enough information to show that the rotation about C of 180 of L equals L prime. Well, let's draw a circle first, and let's see if we can figure it out. There we go. We've crossed through P and A like we should have. Life is grand. Okay. So what is the image of segment AP? Okay, AP. If I put my pencil on AP, we have AP. P is the purple eraser at the tip. AP. So the image of segment AP, if I rotate it 180, is PA, right? In particular, what is the image of point A? So if point A is the lead, if I rotate it 180, the image of the lead is P. Why are the points Q and the rotation about C of 180 of B on the same side of AP? Okay, this is a little bit confusing. Why are the points Q and the rotation of 180 about C? I've got B right there. So why are the points Q and the rotation about C of 180 of B on the same side of AP? So Q and the rotation of B, 180, are on the same side of AP. I mean, technically I can say because, but we would say rotation by 180 degrees maps AP onto itself. I shouldn't put a period there because line AP contains center C. And we are rotating about C. Okay, so the rotation of 1/2 of the map about line AP rotates the other half of the plane. Sorry, the rotation of 1/2 of the plane about line AP maps the other half of the plane onto itself. So B maps onto Q. Okay, B and Q are the same. So B and Q, so B rotated B and Q are in the same plane, half plane, same half plane. Okay, what is the image of the rotation about C of 180 of triangle BAP, which we named BAP2? So what is the image of the rotation about C of 180 of angle 2? It's angle 1, which is angle QPA. It's the same reason. If we have, this is angle 1, angle 2, B, A, P, Q. So it's the same reasoning. If I look at a technical, because under rotation, the vertex of BAP is the same as the vertex of QPA under rotation. So if we're rotating about C 180 degrees, this vertex rotates onto that vertex. So why is the rotation about C 180 degrees of L equal to L prime? Basically, since segment AB maps onto segment PQ, so segment AB maps onto segment PQ. Should have gotten my highlighter out, right? We know that the rotation about C 180 degrees of L, actually I'm going to write that down here, because it's a long little thing. The rotation 180 degrees, the rotation about C 180 degrees of L equals the rotation about C 180 degrees of AB equals PQ equals L prime. So AB rotated 180, the rotation of L, right there, 180 equals the rotation of AB, because AB, the segment AB is on L. So the rotation of L is equal to the rotation of AB, 180, onto PQ, which equals L prime. If we rotate the line, we rotate the segment, onto the segment equals the line. So line equals segment, segment equals line. We've just proven that a rotation by 180 degrees takes L to L prime. By the claim in example 3, lines L and L prime must be parallel, which is summarized below. Here we have our theorem. Suppose a transversal intersects a pair of lines. If a pair of alternate interior angles are equal in measure, then the pair of lines are parallel. That's number 1. Oh, that's funny. Laugh with me, not against me. That's number 1. Okay, discussion. In example 5, suppose we had used a different rotation to construct a line parallel to L that contains P. Such constructions are certainly plentiful. For example, for every other point D on line L, if we still have line L, we talked about points A and points B. What if we have any point D on that line? We can find the midpoint of a segment PD, so we had P up here. We can find the midpoint of segment PD and use the construction example 2 to construct a different 180 rotation. Using our compass, we can do another circle, PD, center C, diameter PD, around a different center such that the image of line L is parallel line through point P. Are any of these parallel lines through P different? In other words, can we draw a line other than the line L prime through P that never meets L? If we look at our first construction, I could have made, actually that's not our first one. If we look at our first one, I've lost our first one. That's hilarious. This is when I should push pause and look for it, right? There we go. Okay, the first thing we said was to label a point A. If I had labeled point D way down there, I would still find my center, and I would still end up with a line on P parallel. Okay, it doesn't matter where I drew this point, anywhere there. Okay, can we draw a line other than line L through P that never meets L? The answer is no, but if you keep reading, you may laugh a little bit or be surprised. The answer may surprise you. It's stumped mathematicians and physics for centuries. Centuries are hundreds of years, right? In nature, the answer is that sometimes possible and sometimes not. This is because there are places in the universe, near massive stars for example, where the model geometry of space is not plane-like or flat, but is actually quite curved. To rule out these other types of strange but beautiful geometries, we must assume that the answer to the previous question is only one line. That choice becomes one of our geometry assumptions. The parallel postulate. Through a given external point, there is at most one line parallel to a given line. In other words, we assume that for any point P in the same plane, not lying on line L, every other line in that plane that contains P intersects L except at most one line. That one line we call parallel to L, okay? We study plane geometry here. And it is nothing like plane, okay? We study everything that's in a plane. We don't do curves like in space. That's something for if you decide to go into that field outside of high school. All right, example 6. We can use the parallel postulate to prove the second part of the basic fact. We finished the first, we're moving on to the second. So the theorem is, suppose a transversal intersects a pair of lines. If the pair of lines are parallel, then the pair of alternate interior angles are equal in measure. All right, proof. Suppose that a transversal AP intersects line L at A and L prime at P. Pick and label another point B on line L and choose a point Q on line L prime on the opposite side of AP. So B is over here, Q is over there. The picture might look a little like the figure below. Let C be the midpoint of segment AP and apply rotation by 180 degrees around center C. As in previous discussions, the image of L is the line rotated at about C 180 degrees of L, which is parallel to L and contains point P. Okay, right there. Since L prime and the rotation of L are both parallel to L, so since L prime and the rotation of L are both parallel to L and contain P, by the parallel postulate they must be the same line. Duh. The rotation about C of 180 of L equals L prime. In particular, the rotation about C 180 degrees of angle BAP, which we've labeled 2 in the past, and QPA, which we labeled 1, are equal in measure. Since rotations preserve angle measures, the measure of BAP, measure of angle 2, is equal to the measure of angle QPA, which was angle 1, which is what we needed to show. Awesome. Okay, please review your relevant vocabulary. It's very important. You can push pause and review it. And then please review what we did in closing. Okay, it's just a restating of what we've learned in the lesson. Good job. It was a tough one today. Nice work.